Welcome, and thank you for joining this executive summary webinar, Invisible Power, Infinite Scale, How Ambient Energy is Powering the Battery-Free IoT World, prepared by Alpert Research Team.
We're talking about what feels like the next huge frontier in wireless, the idea of 1 trillion connected devices.
For years, that's been the vision, tracking every package, every single component in a machine.
But that vision has always had this one tiny little roadblock, the battery.
It's the ultimate bottleneck. I mean, think about the maintenance cost, the sheer cost of swapping out billions of batteries, not to mention the environmental impact. The whole model just hits a wall.
So you can't scale with something that needs to be replaced.
We needed a total shift in thinking.
And that shift is ambient IoT, AIoT.
AIoT is all built around this one core idea, near-zero energy communication, NZEC for short.
We're talking about devices that have to run on a peak power budget of, say, 1 microwatt up to maybe a few hundred microwatts.
How is that even possible?
It's only possible if you completely rethink the architecture. You have to strip out every power-hungry component and really move the intelligence off the device itself.
You're saying there are 3 pillars here: energy harvesting, this new ultra-low power communication, and something called intermittent computing.
And if any one of them fails, the whole system just doesn't work.
When we say battery-free, what are we actually talking about?
Right, that's a crucial distinction. It really means one of two things. Either a device is completely batteryless, it's running off a tiny capacitor, a CSC, or it has very limited storage, like a supercapacitor, just to handle a quick burst of energy it might need.
So why is a tiny capacitor better than tiny lithium-ion battery?
It comes down to 2 things: size and lifespan. First, these capacitors let you build tags that are small enough to be printed right onto a label. But the real kicker is the cycle life.
How many times it can be charged and discharged?
A good chemical battery gives you maybe a few thousand cycles, these CSCs. We're talking millions of cycles.
Okay, so that's how you get a device that you can literally embed in a wall and just forget about for decades.
That's the key. It makes the device truly permanent.
Okay, so let's dig into the first pillar, energy harvesting. EH. We're talking about converting the ambient energy that's just all around us, light, vibrations, into usable electricity.
And the fact that the supply is so unpredictable is what makes it such an immense engineering challenge. But harvesting means you have to optimize for 3 key performance indicators, or KPIs, all under these variable conditions. First is power density,
How much power can you squeeze out of it?
relative to its physical size. And these devices are tiny, maybe 1 millimeter squared. So this is absolutely critical.
And the second KPI?
Conversion efficiency. What percentage of the energy that hits the device, be it light or an RF wave, is actually converted into useful electricity?
And finally,
Dynamic range. The harvester has to maintain its high efficiency across a really wide spectrum of input energy levels, from very, very weak to relatively strong.
okay, let's talk sources. Light seems to be the big one, photovoltaics. But we're not talking about big solar panels in the sun.
No, the real challenge is low-intensity indoor light. A warehouse or an office might only have 100 to 500 lux. Standard silicon solar cells are just not very good at that.
So what's the solution?
It's a new material chemistry called organic photovoltaics, or OPV. The beauty of OPV is that you can chemically tune it to be super efficient at absorbing the specific light spectrum that comes from indoor LEDs. It turns a weakness into a major strength.
RF energy, harvesting power from radio waves.
It's for places where there's no light, no vibration, nothing. Think inside a sealed metal shipping container.
But the power levels must be incredibly low.
They are. That's the trade-off. You generally need a signal strength of at least negative 20 dBm, that's about 10 microwatts, to make it work well. Any weaker, you spend all your time just trying to charge up.
And this is where things like SWIFT come in.
Exactly. Simultaneous wireless information and power transfer. The same signal that carries the data also provides the power for the tag to operate. Thermal energy generators, or TEGs, they use a temperature difference to create voltage. It's called the Seebeck effect. They're great for industrial waste heat or even wearable sensors powered by body heat.
But you need that stable, sustained temperature difference.
You do, and their efficiency is pretty low. Kinetic harvesters, on the other hand, use motion or vibration. They are perfect for machinery monitoring. You embed the sensor on a vibrating motor, and that motion perpetually powers the diagnostics.
Zero maintenance, zero downtime. Pillar 2, communication. With a microwatt budget, you can't exactly broadcast a powerful signal. This brings us to backscatter.
And the whole idea of backscatter is to be passive. Instead of generating its own signal, which is very energy expensive, the device just reflects a signal that's already in the air. And the most efficient version is ambient backscattering, where it's reflecting signals that are just there anyway, like from your Wi-Fi router or a cell tower. It doesn't even need a dedicated signal source.
To get the power that low, the receiver on the tag itself must be incredibly simple.
The simplest ones use something called RF envelope detection. It's basically just a diode and a capacitor. We've thrown out all the power-hungry parts like oscillators and phase-locked loops. That's how you get down into that few microwatt range.
But that simplicity has to come with a huge trade-off.
Because the signal travels from the reader to the tag and then has to bounce all the way back, the signal strength just falls off a cliff. It follows an inverse fourth power law, which means the sensitivity is terrible, around Monica 40 dBm, and it's incredibly easy to jam. If you just turn on your 5G phone next to one of these tags, its powerful signal could completely blind the tag's simple receiver.
So the tag is simple, which means the network has to become incredibly smart to compensate.
That's the whole architectural shift. All the complexity moves to the network.
For example, the tag can't even keep time properly. Internal clock is cheap and drifts all over the place. How does the reader even know when to listen for a signal?
It doesn't. So the network has to force it. It sends out a special signal, a preamble, called the Reader Triggered Acquisition Signal, or RTAS.
Okay, what does that do?
It does two things at once. It gives the tag a temporary, instantaneous clock to sync to, and it sets the power threshold, so the tag's simple receiver knows what counts as a 1 and what counts as a 0.
And then how do you manage hundreds of these tags in a warehouse all trying to talk at once?
So you use a technique called coded backscatter, multiple access, or CBMA. The idea is simple though. The reader gives each tag a unique secret code. The tags all transmit at the same time, kind of shouting over each other, but the powerful reader uses those codes to digitally separate all the mixed up signals.
So the network infrastructure needs an upgrade too.
You rely on what are called assist nodes. These are smaller, local nodes that provide a stronger signal closer to the tags for them to reflect. They also help filter out interference.
And all of this is managed by a new brain in the network core.
The AIoT function, or AIOTF, it handles all the heavy lifting for security and translation because the tags themselves are too simple to run complex encryption.
Which brings us to pillar 3, the software, intermittent computing. If the power can just blink off at any moment, how do you not lose all your work and waste that precious energy?
That's the core software problem.
So what's the single biggest threat in that reality?
Losing computational progress. We call it lost work. The risk is that the capacitor's voltage drops below the shutdown threshold. We call it VFO, before a task is finished.
And if that happens,
The system has to waste all the energy it just spent and restart the entire task from scratch once the power comes back. A huge waste. And the main technique to solve it is called checkpointing. The device periodically saves its entire state, what it was doing, all its data, to permanent memory. When power comes back, it just reloads from that last checkpoint instead of starting all over.
is there a downside?
It costs energy to save that checkpoint. It adds about a 10% energy overhead, but that's a much better trade-off than losing all your progress.
But the truly game-changing approach moves beyond just reacting. It's about proactive intelligence.
Energy-aware scheduling, or EAS. Instead of waiting for the power to drop, you try to predict when a failure might happen. EAS uses a smart scheduler that's coupled with an energy predictor. The application code has to be written for this. It's called task decomposition. Every step is assigned dependencies and an estimated energy requirement.
And the goal is to just avoid scheduling anything that might cause a brownout.
You avoid any execution window that would drain the capacitor below that critical VFO level.
How can a tiny microcontroller running on microwatts handle that kind of complex predictive modeling? Doesn't the computation itself drain the tiny energy budget?
The really heavy, complex modeling predicting ambient energy fluctuations, optimizing the schedule, that's often done offline. In the cloud, the tiny microcontroller only has to execute a much simpler pre-computed optimal policy. It essentially gets its daily action plan from the cloud.
So let's look at the use cases. The value here seems to be unlocked by that combination of massive scale and zero maintenance.
It fundamentally changes the unit of tracking. We move from tracking shipments at the pallet or the box level to continuous item level tracking. Imagine a sensor costing just pennies on every bottle, every box of cereal, every piece of fruit. You can track its environment and location with 1 to 3 meter accuracy right from the farm to the store shelf.
That level of detail was just cost prohibitive before?
Completely, because of the battery cost and the disposal nightmare.
And what about in the industrial sector?
It enables predictive maintenance at an unprecedented scale. Instead of time-based maintenance, you embed a sensor powered by the machine's own vibration directly onto a critical bearing or valve.
And since it never needs service?
It can continuously report on the machine's health. Staff can spot a potential failure signature weeks in advance. That zero maintenance capability can save fortunes in avoided downtime.
Smart shelves in retail.
Tags are built right into the product packaging. The shelf knows in real time exactly what its inventory is. No more manual scanning, fewer out-of-stock items.
For any of this to work at scale, it needs to be standardized.
And we're seeing incredible fast-paced convergence. intelligence. 3GPP Release 19 is building this directly into the 5G standard, i.e. is creating a Wi-Fi standard for it, 802.11 BP. Even Bluetooth is getting involved. Everyone is getting on board.
Looking further out, this feels like a foundational step toward that 6G vision of ambient intelligence.
6G concepts like intelligent reflecting surfaces, basically smart mirrors that can focus RF energy, seem almost designed to solve the weak signal problem for backscatter. They can help steer and amplify these faint reflections.
What are the biggest technical hurdles we still need to clear for this to become truly mainstream?
I'd say there are two big ones. First is what's called the charge delay ambiguity. If you're trying to calculate location based on signal timing, you don't know how long the tag had to wait to charge up before it replied. That delay messes up your calculation.
And the second one.
It's that near-far problem we touched on. How do you stop a simple, sensitive tag from being totally blinded by a powerful 5G phone right next to it? Solving that interference is critical for reliability.
It seems like the whole story here isn't about inventing a better battery. It's an architectural revolution. The genius is in making the endpoint device as simple as possible and pushing all the complexity, the timing, the security, the intelligence into the network core.
That's it. You solve the battery problem by designing around it entirely. And that shift has this really profound strategic implication to think about. As these trillions of tags start drawing power directly from ambient RF signals, what does the telco become?
They're not just selling data anymore.
They could become RF energy utilities, selling power as a service to fuel this massive, invisible world of connected devices. I think the key strategic takeaway is that shift in market dynamics. This technology fundamentally transforms what used to be an operational cost for a network operator, blasting out a radio signal, into a monetizable service, providing wireless power. This movement creates new ecosystems where the manufacturers and retailers who actually own the sensor data become the new data hubs. They create value in a way that's separate from just providing connectivity. It forces a total reassessment of where value lies in the entire IoT chain. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.